Yeah.
Rolling.
Okay. Right. I want to take you through paper A. It's another controlled assessment. There's 5 questions. Same as the other one, so it's 6 out of 10 to pass. I've got Alex, my lad, here videoing.
Hello.
If he doesn't understand, he's going to chip in, because if he don't get it, I guess you won't get it, and that's how we'll go. So it's a bit like the other ones in that there's a couple of high value questions that's probably worth getting right, and a couple of easy ones. So the first ones are fairly simple in that they talk about inputs and outputs, and it turns out that there is an electrical standard IEC 61131-3 that there must be people alive who've actually heard of. I haven't heard of it anyway, but that kind of defines how you define PLC inputs and outputs. Yeah. So nothing too surprising here. If somebody asked you to say what the 3rd, 4th or 5th PLC output was, we've been writing them down as percentage I, and then it might be worth making it like a proper I. So 0.1 is the first one. Now I think we've been using 0.0 on these Siemens PLCs as the first one, but when they're doing it, 0.1's the first one, and so 0.2, oh hang on, I've missed my percentage out. Percentage I 0.2 is your second one, and so on forever, yeah? And outputs, I hope nobody is surprised by, come out much the same. So your first output is Q, of course it's an output, 0.1, yeah, and so on. There's a mark for each of those, so it'd be hard to get wrong, but equally it might be it's a couple of easy marks, isn't it? And Lee's gonna give you this paper after break. That's the plan. So this video is me not being there but talking to you, and then the other one is how inputs are wired up on a PLC, and this gets a bit techie nerdy, but all you've got to really do is draw the standard input circuit that's actually built inside the PLC that you've never seen and I've never seen, but I do know a little bit about how they work, so I'll talk you through it now. First thing you've got is a power supply in the PLC kicking out 24 volt DC, yeah, we know that, we've been using that quite a lot. I'm just going to call it PS on their power supply, yeah. And then out of there comes 24 volts, very nice. And somewhere along the line we've got an input device, whatever it is, and it could be running potentially at high voltage, but in this case it's 24 volts. Yeah. And then what we've got is what's called a potential divider here, and a potential divider is usually 2 resistors. Now they've drawn it a bit weird. I'd normally draw them in a straight line, but anyway, they've drawn it like this, and these are resistors, right? And sorry, that's not very good. That's R1 and that's R2. 2 resistors. What they do is divide up this 24 volts, which I should have written on here, yeah, into a smaller voltage. What they're doing, I don't know if you do know, but LEDs, which are forming our next bit over here, blow up if they get more than 5 volts in them, basically. And we've got one LED pointing that way, and that's the symbol. That's actually a symbol for a diode. I'll explain why it's an LED in a minute and what they're actually doing here. And we've got something called S/S here. That stands for sinking and sourcing. What that means is you can decide whether the PLC is working as a hole for current or is working as a place that you can pull current through. And so they draw a dotted line here. What that means is you might connect sinking and sourcing to 24 volts, or you might connect it to 0 volts, which is down here, and that's going back to my power supply, which I'm now going to try and draw much better than I have. So it has to skip over there, yeah, and it has to skip over there. We've done that before, yeah. And I'm going to come down here and I'm going to put me 0 volts in there, right? So I could connect sinking and sourcing to 24 volts. I could connect it to 0 volts, and I'm not going to get very far unless I connect R2 in there.
And sinking and sourcing would work no matter what you connect it to? Or?
Yeah, it's just, we're going to talk about the actual transistors that you could use, the sensors that we could use, and some of them are sinking sensors and some of them are sourcing sensors. We're going to talk about them in a minute.
Cool.
So I've also got another LED there, and that's because you could connect it one way or you could connect it the other way. Either way it's going to get 5 volts. Now this wiggly line here with an arrow on it, that's light, right? That light is shining on what's called a phototransistor. A phototransistor, and we'll talk about transistors a bit in a minute, when you shine light on it, basically it starts to conduct electricity that way. Yeah? Can you see that because it changes from electricity over here to electricity over here, it's what's called decoupled. You talk about this as an opto-isolator. There's a physical gap between this side of the circuit and that side of the circuit, which stops you blowing the PLC up, which is good news. And then over here, we've got some more stuff. It's what's called a debouncer and a filter. I don't quite understand this, but I sort of do. We've got a capacitor in there. Think of a capacitor as an electrical bucket, right? Long story short, if we get spurious signals coming through on here, this filter section, R3 and R4, and it's calling it C1, yeah, capacitor 1. They work as a debouncing filter. I think it's a low pass filter, but I don't know enough about quite how that works to understand. But all you need to know is it stops the circuit picking up spurious signals from over here. If your voltage is just flicking around a bit, yeah, it would still, this light might be flicking around a bit, but until you get a big long signal, nothing's getting through this filter. That is what you need to draw on this test, yeah. If you haven't done, draw it down. There's also a PowerPoint on here which has got this in it, but maybe drawing that will make you remember it better. Right, there's 2 more bits to talk about, and that's inputs and outputs. So I'm going to tear this one off and do the next one. Alright, you can have inputs. I talked about sinking and sourcing before, and it's about how you set the PLC up to work. I think I've got the world's supply of emails coming through if you're wondering what the noise is. Right, we had an opto transistor before, a transistor that turns on due to light. You've seen all those optical sensors that we've got downstairs in the workshop in 003. So I'm assuming that the optical sensors, when you wave your hand over it and it goes high, are optical transistors. But there's all sorts of ways of turning a transistor on. In my world, all that matters is that you've got a sensitive leg on a transistor called the base. And there's two types of transistor, what's called a PNP, and there's another type called an NPN. I'll draw the NPN one in a minute. You've got to draw both of these on the test. I'm going to draw a PLC input here, and I'm going to draw things that you haven't seen before. The first thing is 24 volts. Well, you've seen that before. And down here I've got 0 volts, and you've seen that before. Then I've got X. So that just means an input. Quite why they haven't called it I, like they do everywhere else, well, I don't know. And then you've got S and S, and I think we've touched on that. That's sinking or sourcing. What that terminal on your input does is decide whether it's going to be a sinking input or a sourcing input. So in this case, I'm going to connect it to 0 volts. Yeah? And this one's going to be sinking. So I'm just looking at what the question asks you, so that I don't give you duff information. Yeah, it asks you to draw a PNP and an NPN. It doesn't ask you to say whether they're sinking or sourcing, but it helps me to understand what I'm doing, so that's why I'm putting it on here. Transistors have got two other legs. One's called an emitter. Sometimes gets abbreviated to E, in fact it almost usually does. And the other one's called a collector, and that gets abbreviated to C. In this case, the collector is the one that's going in to the input. Can you see the current is going into here? Because we've connected it to 0 volts, it's going to be sinking. You've got to imagine this is a big electrical hole into which we can pour electricity. The other side is going to be connected to 24 volts. Yeah? So it's going to take power from here and it's going to drop it into the input. So the input's now connected to 0 volts via sinking and sourcing, and so this will work as a whole. The other way of connecting it up is what's called sourcing. So I'm going to draw the same thing again, yeah, for an NPN sensor. So some sensors are PNP sensors, yeah, and some sensors are NPN. It actually works. Well, I'll draw the NPN one and maybe explain to you what's going on. So I'll draw the same connections I had before, 24 volts and X, and sinking and sourcing, and 0 volts. But this time, I'm going to connect sinking and sourcing to 24 volts. Can you see that this time we are going to pull the power from the input rather than use it as a whole? So this one's sourcing. Okay, I've got a transistor again, but this time it's an NPN transistor, so the symbol is subtly different. It might have helped if I'd drawn the other one slightly better, but anyway, look, the arrow goes that way. Can you see that the emitter leg's now at the bottom? On the PNP, the emitter leg was at the top. The collector leg goes at the top. They change places, and this time, give me a little jumpy over, we go into X. This time the current will flow from the input down through the emitter into 0 volts. So that's reasonable. The reason I was whinging is I'm not sure you can see that arrowhead on there very well. I don't know how well I've drawn it. And then the base leg is here. It's probably just worth talking about what actually happens here. Okay, on a PNP, whatever voltage is at the emitter, when the base voltage goes 0.7 of a volt lower, this turns on. Yeah, so it starts to flow. So in principle, you'd think, well, if the voltage here ever goes to 23.7 volts or lower, this transistor turns on and the input starts to read high. Yeah, it's not quite what happens, because you'll find that the sensors are actually set up. They play tricks in the circuits in the sensors. There's more stuff going on, and most of these wouldn't read as high until the voltage went perhaps below 12 or even below 8. Yeah, but inside there somewhere there is a PNP transistor that is becoming what's called forward biased when the base voltage drops below 23.7. The NPN works the other way round. Because the emitter's already at 0 volts, when the base voltage goes above 0.7 of a volt, this one starts to turn on. That's about how the transistors work. The sensor will be different. So some sensors, I don't know if it's optical or whatever, temperature sensors or pressure sensors, might be more suited to using an NPN style transistor. And some sensors might be more suited to using a PNP type transistor. On the basis that I'm not going to be there while you're doing this, I'm going to ask Alex if that was clear.
Possibly. I think it was.
Do you? Alright. Okay. So that's what you need to reproduce. You need to reproduce... Hang on, let me get the right one. That circuit diagram here, well, we talked about inputs and outputs. That's question 1. That's question 2. This is question 3. And I think there's only 4 questions. Yeah, there is. So there's 4 marks for that one. Yeah? A mark there, a mark there. And there's 4 marks, 2 and 2, for drawing those. That's it really. If you can draw them and label them, you should get 10 out of 10. And Lee's going to give you the papers, and he'll stick them on my desk and I'll mark them when I get back. Right, I think you're supposed to say, if you'd like to subscribe to my channel,
click the bell.
Click the bell or something, I don't know, it's all beyond me. Anyway, cheers for listening. Ta-ra.